Hello there, and welcome to Space Science Before Sleep, where the universe grows quiet, curiosity moves gently, and science takes its time beneath the stars. Tonight we're going to descend beneath Europa's frozen surface and explore a moon that seems at first glance to have hidden everything important behind a silent wall of ice. From far away, Europa looks smooth, bright, and almost untouched, a small pale sphere moving through the immense shadow of Jupiter. Yet its surface is crossed by long reddish fractures, broken plains, and strange regions where the ice appears to have shifted, rotated, and frozen again. This is the contradiction at the heart of Europa. It looks sealed, but it may not be still. Beneath the frozen exterior, the evidence strongly suggests a global ocean of salty liquid water, kept from freezing completely by heat generated inside the moon. That answer sounds simple until we ask what lies between the surface and the sea, how the water remains liquid so far from the sun, whether material can move through the ice, and whether the hidden ocean contains the chemistry and energy required for life. We will take those questions slowly, beginning not in the ocean, but above it, where the moon first reveals itself through light. Perhaps Europa is visible from your room tonight, though not as a moon you could easily recognize with the unaided eye. Jupiter may appear as a bright, steady point somewhere beyond the window, and Europa would be one of several tiny companions gathered close beside it, visible through a modest telescope as a speck of light. That speck is a world slightly smaller than Earth's moon, with almost no atmosphere to soften its landscape and no blue sky above the ice. Sunlight reaches it but weakly. The surface remains intensely cold. From this distance, Europa could seem like a frozen relic, a place where change ended long ago. But planetary surfaces are excellent witnesses even when they are not especially talkative. Craters reveal age, fractures reveal stress, colors reveal composition, shapes reveal movement. Europa's surface contains relatively few large impact scars compared with many other icy moons, suggesting that older terrain has been altered or replaced. Something has renewed parts of this frozen world. The universe, as usual, has neglected to leave a convenient maintenance report. Before we drift any farther, I'd love to know where in the world you're listening from tonight and what time it is there. And if these slow journeys through space help you relax, learn something new, or simply feel a little less alone beneath the night sky, I'd be grateful if you like the video and subscribe to Space Science Before Sleep. It helps this quiet corner reach more curious minds who may need something gentle at the end of the day. What would you most hope to find beneath Europa's ice? Unusual chemistry, active geology, or signs of life? There is no need to choose the most scientific answer. Curiosity is allowed to be personal. A hidden ocean is already an invitation to wonder even before we know what it contains. Now let the room around you become a little quieter. Settle into the pillow, allow your shoulders to loosen, and let the details pass without any need to hold on to them. There will be no test at the end, and missing a few measurements somewhere along the journey will not prevent the ocean from being there. We can simply follow the questions. How thick is Europa's frozen shell? Is it one rigid layer, or does warmer ice move slowly beneath the brittle surface? Why do some regions look as though enormous blocks have broken apart and shifted position? Can salts or other chemicals travel upward from the ocean? Can radiation-made compounds move downward from the surface? And at the deepest boundary where water may touch rock, could chemical energy persist for billions of years? These questions lead toward life, but they do not begin with life. They begin with ice gravity and the patient reading of clues. To understand Europa, we first have to place it inside the gravitational machinery of Jupiter's moon system. Europa does not travel alone. It moves in a regular orbital relationship with two neighbouring moons, Io and Ganymede, whose repeated gravitational pulls help prevent Europa's orbit from becoming perfectly circular. As Europa approaches and recedes from Jupiter during each orbit, the strength and direction of Jupiter's tidal influence change slightly. The result is a continuous flexing of the Moon's interior. Europa is not squeezed dramatically like an object in a hand. The deformation is small compared with the Moon's total size, but it repeats orbit after orbit across immense spans of time. Materials inside Europa resist that motion, and some of the mechanical energy is converted into heat. This tidal heating is one of the main reasons scientists think liquid water can survive beneath the ice, despite the weak sunlight and deep cold. Jupiter does not warm Europa like a lamp. Gravity performs the slower work from within. That internal warmth does not mean the surface becomes comfortable. The uppermost ice remains exposed to space and to energetic particles trapped in Jupiter's powerful magnetic environment. From above, the shell is cold, rigid, and chemically altered by radiation. Deeper down conditions may gradually change. Ice under greater pressure and at higher temperature can behave less like brittle glass and more like an extremely slow-moving solid. Glacial ice on Earth offers a useful comparison. A glacier remains frozen, yet it can flow over years and centuries. Europa's shell may also deform, circulate, fracture and heal, although the lower gravity, colder surface, unknown impurities and tidal stresses make it a different system entirely. We should not picture a perfectly smooth lid floating above an open sea. The shell may contain several mechanical regions, pockets of salt-rich material, old fractures, warm rising ice, and perhaps temporary areas of partial melting. We do not yet know how these possibilities are arranged or whether they occur everywhere. For now, one simple image is enough. Picture Europa as a pale moon crossed by a single dark fracture. Above that line lies space radiation and frost. Within it may lie salt's disrupted ice and evidence of movement. Far below it, hidden beyond any human view, is the ocean inferred from the way Europa responds to Jupiter's magnetic field and from the restless geology written across its surface. We cannot yet follow the fracture all the way downward. It may not connect directly to the sea at all, but it tells us that the frozen exterior is not merely a blank covering. It is a record of forces working below. In the next part of our descent, we will move closer to those ridges, bands, and shattered plains, and learn how scientists read a landscape that has been rewritten without ever becoming warm. Europa's surface is not a frozen blank. It is a record written in fractures, ridges, dark bands, and patches of terrain that seem to have been taken apart and assembled again. From a great distance, the moon looks almost smooth, because its mountains and deep impact basins are modest compared with those on many other worlds. Closer views tell a different story. Long lines curve across the ice for hundreds or even thousands of kilometers. Some appear as pairs of raised ridges with a darker groove between them. Others widen into broad bands where older ground seems to have separated and new material filled the space. These markings overlap one another, so their relative ages can sometimes be reconstructed like pencil lines drawn across the same page. A younger fracture cuts through an older one. A band interrupts a plane. A crater arrives later and leaves its circular scar over everything beneath it. Europa does not provide dates beside these events, which is inconsiderate but fairly normal for a moon. Instead, scientists read sequence, shape, colour and texture. One of the most striking features of Europa is what its surface lacks. There are impact craters, but not nearly as many large ancient scars as we might expect, on a surface that had remained unchanged for most of solar system history. Small worlds without active geology often preserve a crowded archive of collisions. Europa's archive appears to have been edited. Some older features may have been buried, distorted, broken apart, or replaced by younger ice. Counting craters cannot give a perfectly simple age because the impact rate itself must be modelled, and different parts of Europa may have been renewed at different times. Even so, the broad conclusion is strong. The visible surface is geologically young compared with the age of the Moon itself. This does not mean that all of Europa was resurfaced in one dramatic global event. The renewal may have occurred gradually region by region through many different processes. The ice we see is therefore less like an untouched shell, and more like the latest surviving pages of a very long book, with most of the earlier chapters hidden underneath. Across those pages run Europa's famous lineae, the dark linear markings that give the Moon its cracked appearance. Some are narrow fractures, some are complex systems of ridges, some are broad enough to contain their own internal patterns. Their reddish-brown colours probably come from materials mixed with the water ice, perhaps salt sulfur-bearing compounds, or other substances altered by the harsh radiation around Jupiter. The exact composition is still being investigated, partly because energetic particles can chemically transform whatever reaches the surface. A material that began below as one compound may no longer look the same after years of exposure. The double ridges are especially intriguing. They often consist of two nearly parallel raised walls separated by a central trough, as though the surface split and then built up along both edges. Several mechanisms might create them. Repeated opening and closing of fractures could move warm ice or briny material upward. Pressure changes beneath the surface might deform the ice. Shallow liquid pockets could sometimes contribute. No single explanation has yet been proven to account for every ridge, and Europa may be under no obligation to use only one construction method. Broader bands suggest even larger movements. In some places, the patterns on opposite sides of a band appear as though they once fitted together before the surface pulled apart. Newer material seems to occupy the gap between them. The visual resemblance to seafloor spreading on Earth is tempting two sides separate, and material rises between them. But the comparison must be handled carefully. Europa has no confirmed system of rocky tectonic plates like Earth's, and the material involved is ice rather than hot mantle rock. The forces, temperatures, and timescales are different. Still, the matching edges imply extension, meaning the icy surface was stretched. If some regions opened, other regions may have had to compress or disappear elsewhere unless Europa's shell expanded overall. Scientists have proposed several possibilities, including places where one section of ice may have moved beneath another, but the evidence remains incomplete. What matters for our descent is that the shell has behaved as a mobile material. It has not simply rested above the ocean like a perfectly fitted lid. It has been pulled, shifted, fractured, and perhaps recycled. Then there are the landscapes known as chaos terrain, where Europa's orderly lines give way to something far more disrupted. Large blocks of older ice appear tilted, rotated, or displaced within rougher material. Some regions look faintly like broken sea ice that drifted and froze again. Yet that familiar image can mislead us. Europa's blocks may not have floated freely on a shallow open ocean. The global sea could lie far below, separated from the surface by a substantial shell. Chaos terrain might instead form when warmer ice rises slowly from below, softening and deforming the upper layers. Local pockets of melt or salty liquid may weaken the shell. Tidal stresses may break the surface while heat changes the ice beneath it. Several of these processes could work together, and different chaos regions may have different histories. The scattered blocks are therefore clues to disturbance, but not a direct photograph of the hidden ocean. They show that something changed inside the shell. They do not yet tell us precisely how deep that change began. Pit's domes and darker spots add smaller details to the same mystery. Some depressions may mark places where near-surface ice collapsed or where warmer material altered the layers below. Rounded-up lifts may have formed as buoyant masses of relatively warm ice rose slowly upward, rather like thick material moving through an even thicker surrounding medium. The motion would be extraordinarily slow by human standards, but geological time is patient. Salt or other impurities could lower the melting temperature locally, allowing small amounts of liquid to exist, under conditions where pure water would remain frozen. These possible reservoirs are sometimes described as lakes within the shell, though that word may suggest clean open bodies of water more familiar than anything likely to exist there. They might instead be thin lenses of brine networks of partially melted ice, or temporary pockets that freeze and reform. Their existence, depth, and duration remain uncertain. Even so, they could matter greatly because they might provide intermediate steps between the irradiated surface and the much deeper ocean. The surface therefore gives us a careful but incomplete answer. Europa has changed. Its shell has cracked, stretched, shifted, and renewed itself. Some material has risen or been exposed, though we cannot assume that every dark band carries water directly from the global sea. Some parts of the ice may connect only to shallow regions within the shell. Others may preserve chemistry that began deeper down, but was transformed during its journey upward. To understand why so much movement is possible, we must now step away from the individual fractures and look at the force acting on the entire moon. Europa circles a planet more than 300 times its own mass, while neighbouring moons repeatedly adjust its orbit through gravity. The lines beneath us are not random scratches. They are part of a larger rhythm. In the next stage of the journey, we will follow that rhythm around Jupiter and see how gravity can keep a frozen world moving from the inside. Europa's fractures are not merely scars left behind by an old event. They are signs of a rhythm that continues every time the moon travels around Jupiter. From the surface, Jupiter would dominate the sky, hanging enormous and striped above the horizon. Europa is tidally locked, so the same side of the moon generally faces the planet, just as the same side of our moon faces Earth. But Europa's orbit is not a perfect circle. Its distance from Jupiter changes slightly as it moves, and that small variation is enough to make the planet's gravitational pull grow stronger and weaker in a repeating cycle. The moon is stretched a little more when it is closer, and allowed to relax a little when it is farther away. Nothing about this movement would look dramatic to an observer standing safely above the ice. Europa does not visibly pulse like a balloon. Yet throughout its interior, rock and ice respond to a gravitational tide that never quite stops. A tide is simply a difference in gravity across an object. Jupiter pulls more strongly on Europa's near side than on its far side because the near side is slightly closer. That difference stretches the moon along the direction toward Jupiter and compresses it in other directions. If Europa followed a perfectly circular orbit and remained in a completely steady configuration, the shape of this tidal bulge would change very little. But the orbit remains slightly eccentric, and the orientation and strength of the tidal stresses vary as Europa moves around the planet. The shell is repeatedly bent and distorted. One useful comparison is a piece of stiff material flexed back and forth. Some of the mechanical energy becomes heat because the material does not respond with perfect efficiency. Europa is not being folded by invisible hands, and its interior is much more complicated than any object held in a room, but the basic principle is similar. Repeated deformation can warm a body from within. Europa's eccentric orbit does not persist by accident. Left alone, tidal interactions with Jupiter would gradually tend to make the orbit more circular, reducing the changing stresses and much of the internal heating. But Europa is not alone. It participates in an orbital resonance with Io and Ganymede, two of Jupiter's other large moons. Their orbital periods are linked in a repeating pattern. For every orbit completed by Ganymede, Europa completes about 2, while Io completes about 4. This regular timing means the moons repeatedly return to particular arrangements and tug on one another in a coordinated way. Their gravity continually prevents Europa's orbit from settling into a perfect circle. The resonance acts rather like a carefully timed push given to a swing, although no one is choosing the timing and the swing in question is an entire moon. The result is a long-lived supply of orbital energy that can be transferred into Europa's interior through tidal deformation. The neighbouring moon, Io, shows how powerful this process can become. Io orbits closer to Jupiter and experiences intense tidal heating, enough to support widespread volcanic activity. Europa is not heated as strongly, and its outer layers are made largely of water ice rather than volcanic rock. Still, the same broad gravitational machinery operates there in a gentler form. Heat may be produced within Europa's rocky interior, within the ice shell, or in both regions. Depending on how the moon is structured and how easily its materials deform, the amount of heating is not known with perfect precision. It depends on properties that are difficult to measure remotely, such as the thickness of the shell, the viscosity of the deeper ice, the structure of the rocky mantle, and the way the ocean moves beneath the frozen roof. Even the ocean itself can respond to tides, creating currents, and possibly contributing to the redistribution of energy. A neat diagram can show one bulge and one orbit. The real moon is less tidy. This internally generated warmth does not need to make Europa hot. It only needs to slow or prevent the complete freezing of the water layer below. The outer surface loses heat rapidly to space and remains extremely cold, but ice is also an effective thermal barrier. A thick shell can insulate the ocean beneath it, allowing heat from tidal deformation and radioactive decay in the rocky interior to escape only gradually. Picture a dark ocean covered by a roof that is frozen solid at the top but becomes warmer with depth. Near the surface, the ice may fracture when stresses become too great. Farther down, warmer ice may deform without breaking, flowing over long periods while remaining solid. Between those regions, stress can be stored, released, and redirected. The ridges and bands we saw earlier may be the visible consequences of this hidden response, though connecting any single feature to one precise tidal event is rarely simple. The timing of the stresses may also help explain why fractures appear in different orientations across Europa. As the moon travels around Jupiter, the directions in which the shell is stretched and compressed shift slightly. Over many cycles, fractures can open close or be reactivated. Some models suggest that liquid or warm ice could rise into these openings, building ridges through repeated episodes. Other models emphasize movement within the shell or changes in pressure beneath it. Tidal forces provide the energy and stress, but they do not automatically explain every landscape. The composition of the ice, its temperature, its grain structure, and the presence of salts can all influence where it breaks and how it heals. Two regions experiencing similar gravitational forcing may still develop different features. Europa's surface is therefore not a simple map of Jupiter's pull. It is the result of gravity interacting with a layered and imperfect material over immense spans of time. Keep one quiet image in mind as we leave the orbit behind. Europa moves through darkness while Jupiter rises almost motionless in its sky. The moon follows the same path again and again, yet no orbit is entirely uneventful. Each circuit slightly bends the shell. Each cycle shifts stress through the ice. Each repeated pull helps maintain the warmth hidden below. Gravity, which seems so gentle when it keeps a moon in orbit, is also working inside that moon. turning motion into heat without flame or sunlight. But tidal heating alone does not prove that a global ocean exists. To find the strongest evidence for the water beneath the shell, scientists had to measure something even less visible than the ocean itself. They had to watch how Europa answered a changing magnetic field. The strongest evidence for Europa's ocean did not come from an image of water. It came from an invisible response to an invisible force. When the Galileo spacecraft passed close to Europa, its instruments measured changes in the magnetic environment around the Moon. Jupiter possesses an enormous magnetic field far stronger than Earth's, and Europa travels deep inside it. Because Jupiter's magnetic axis is tilted relative to its rotation, the field experienced by Europa changes regularly as the planet turns. Europa is therefore immersed in a magnetic influence that shifts in direction and strength. If the Moon were only a cold mixture of rock and solid ice, its response would be limited. Instead, Galileo detected a secondary magnetic field associated with Europa itself, one that changed in a way scientists expected from a hidden layer capable of conducting electricity. The Moon seemed to be answering Jupiter's field from somewhere beneath its surface. The principle behind this answer is called electromagnetic induction. A changing magnetic field can create electric currents inside a conductive material. Those currents then generate a magnetic field of their own, partly opposing the change that produced them. The same basic idea appears in electrical generators, transformers and induction cooktops, though Europa is neither a kitchen appliance nor especially useful for preparing dinner. Jupiter supplies the changing external field. Europa supplies the conducting layer. Galileo measured the resulting magnetic response during several close encounters. Scientists then compared the observations with models of different possible interiors. A global layer of electrically conductive liquid provided the most convincing explanation. Water in its pure form is not an especially good conductor, but water containing dissolved salts can carry electric current much more effectively. This is why the measurements point not merely toward liquid but toward an ocean likely containing salts. Imagine a dark room containing a hidden metal ring. You cannot see the ring directly, but if you move a magnet nearby, currents arise in the metal and produce a measurable field. From that reaction, you can infer that something conductive is present. The analogy helps, but Europa is far more complicated. Jupiter's magnetic environment is filled with charged particles and plasma. Europa may possess a thin ionosphere created when surface material is struck and released into space. The geometry changes as the Moon moves, and the spacecraft samples only particular paths rather than observing the entire system at once. Scientists must separate the response of the hidden interior from disturbances in the surrounding plasma. Even so, the induced field detected near Europa fits the behavior expected from a conducting layer extending around much of the Moon. A local pocket of liquid would have difficulty producing the same broad response. A global ocean is therefore the leading interpretation. Magnetic induction tells us a great deal, but it does not tell us everything. The strength and timing of the response depend on several properties at once. The thickness of the conducting layer, its depth beneath the surface, the concentration and type of dissolved salts, and the electrical behavior of the surrounding materials. Different combinations can sometimes produce similar magnetic signatures. A deeper ocean with one conductivity may resemble a shallower ocean with another. Galileo's measurements were also limited by the spacecraft's trajectories and by the complex radiation environment around Jupiter. The data strongly support a conductive subsurface layer, yet they do not provide a simple picture of its shoreline temperature currents or chemistry. The magnetic field reveals presence more clearly than detail. It tells us that something capable of carrying current is hidden below. It does not hand us a labeled cross-section, Other observations make the ocean interpretation more persuasive. Europa's surface geology shows repeated deformation resurfacing and movement that would be easier to explain if the ice shell rested above a mechanically separate layer. Tidal models show that Jupiter's gravity can produce internal heating sufficient to help preserve liquid water under plausible conditions. Europa's overall density indicates that the Moon contains both rocky material and a substantial outer layer rich in water. None of these clues alone proves every detail of the interior. Together, however, they form a consistent picture rock toward the center, a deep layer of a liquid water above it, and an icy shell surrounding the ocean. Science often advances this way. One measurement suggests a possibility, another constrains it. A third makes the alternatives less comfortable. Eventually, the hidden structure becomes the explanation that best allows all the evidence to coexist. The idea of a global ocean changes the meaning of Europa's surface. A fracture is no longer merely a crack in frozen ground. It may be part of a shell moving above liquid water. A disrupted plane may record heat rising through the ice. A dark material exposed along a ridge may have come from within the shell, perhaps carrying chemical information from deeper regions, though its exact origin may be difficult to trace. The ocean also changes the Moon's response to tidal forces. A liquid layer allows the outer shell to move more independently from the rocky interior than it could if the Moon were frozen solid throughout. This separation may affect stress patterns, rotation, and the way fractures develop. The ocean is not simply a hidden container beneath the landscape. It may be one of the reasons the landscape exists in its present form. We should still keep the language careful. No camera has watched waves beneath Europa's ice. No probe has lowered an instrument into the water. The global salty ocean is an inference, but it is an inference supported by several independent lines of evidence, and by the remarkable magnetic reply Galileo recorded as it passed through Jupiter's field. Europa revealed its sea without opening the ice. It allowed the ocean to be detected through electricity motion and gravity. Yet the discovery leaves a practical question suspended above that dark water. How far below the surface does the ocean begin? Between the frozen plains and the liquid layer may lie a shell thicker and more complicated than early images suggested. Our next step is therefore not into the ocean itself, but into its roof, where cold, brittle ice may gradually become warmer, softer, and far more difficult to measure. Europa's ocean may encircle the entire Moon, but reaching it would require crossing a frozen roof whose thickness has been debated for decades. Early interpretations allowed for a relatively thin shell, perhaps only a few kilometers deep in some models. Such a shell could make it easier to imagine water rising toward the surface fractures, opening into shallow reservoirs or chaos terrain, forming directly above the ocean. Other models produced a far thicker shell, extending through tens of kilometers of ice before reaching liquid water. In that picture, the surface and ocean are separated by a substantial planetary layer, with its own internal circulation temperature structure and geological history. Both possibilities could explain parts of Europa's appearance, which made the argument difficult to settle. A fracture at the surface does not reveal how far downward it reaches. A ridge cannot tell us by shape alone whether liquid lies 1 kilometer beneath it or 20. The roof has no exposed edge where its thickness can be measured. It must be examined indirectly. One method begins with temperature. Europa's exposed surface is bitterly cold because it receives weak sunlight and radiates heat into space. The base of the ice shell, where solid ice meets the ocean, must be much warmer close to the temperature at which water remains liquid under those pressures and chemical conditions. Between the surface and the ocean, temperature should generally increase with depth. If heat moves mainly by conduction, passing slowly through solid material without large-scale motion, the steepness of this temperature change can help estimate how much ice is present. A thin conductive shell must carry the difference between cold surface and warm base across a shorter distance. A thick shell spreads that difference across a larger one. It is similar to comparing two walls that separate a warm room from a winter night. The way temperature changes through each wall depends partly on its thickness. Europa's shell naturally is less cooperative than household insulation. Its ice may contain salts, cracks, pores, changing grain structures and regions that move. In September of 2022, NASA's Juno spacecraft passed close to Europa and used an instrument called the microwave radiometer to measure natural microwave energy emerging from beneath the surface. The instrument had been built primarily to study Jupiter's deep atmosphere, but during the flyby it became a remote thermometer for Europa's ice. Different microwave frequencies can carry information from different depths, allowing researchers to compare thermal emissions from shallow and deeper regions. The analysis pointed toward a thermally conductive ice layer averaging about 29 kilometers thick in the region Juno observed, with an uncertainty of roughly 10 kilometers. That is close to 18 miles at the central estimate. It is a substantial distance too far to think of the ocean as lying just beneath a thin frozen skin. Yet the result is regional rather than a complete global map, and it depends on models of how microwaves travel through ice. The measurement narrows the possibilities, it does not close the case. There is also an important distinction between the conductive layer measured by Juno and the total possible thickness of the shell. Heat can move through ice in more than one way. Near Europa's surface, where the ice is extremely cold and rigid conduction is expected to dominate. Deeper down, warmer ice may become soft enough to circulate slowly while remaining solid. Warmer material could rise, lose heat, and descend again in a process called solid-state convection. Nothing would be rushing. A complete cycle might take longer than civilizations last, but geological time has little difficulty with slow appointments. If such a convecting region exists below the cold, conductive layer, the full distance from surface to ocean could be greater than the thickness inferred from the microwave temperature gradient. The Juno observations were not able to determine whether this deeper moving layer is present. Their estimate is therefore best understood as a constraint on the cold, conductive portion in the terrain examined and possibly a lower bound on the total shell. The microwave data also revealed clues about the uppermost ice. The observations were consistent with small scattering features, perhaps cracks, pores, voids, salt inclusions or other irregularities concentrated within the first few hundred meters below the surface. These imperfections appear to be small and shallow compared with the full inferred shell thickness. They may help explain how microwaves are reflected and scattered before escaping into space, but they probably do not form a simple network of open passages extending all the way to the ocean. Europa's visible fractures can be enormous in length, yet a long surface feature need not be deep. A crack in paint may cross an entire wall without passing through the bricks behind it. The comparison is imperfect because Europa's fractures are shaped by tidal stress and changing ice, but it reminds us not to confuse horizontal scale with vertical reach. The surface may be heavily marked while the deeper shell remains difficult to cross. Composition adds another layer of uncertainty. Pure water ice transmits microwaves differently from ice containing salts or other impurities. If the shell is more chemically complex than the idealized models assume, the estimated sounding depths and thickness can shift. Europa is also unlikely to be uniform. Tidal heating may vary with location. Some regions may contain warmer ice, different concentrations of impurities, or structures left by earlier geological activity. The shell itself may have changed thickness over time as Europa's heat production and surface history evolved. Juno observed only a portion of one hemisphere during a brief encounter, so its results should not be stretched into a claim that every point on Europa has precisely the same frozen roof. Future measurements from several instruments and many viewing geometries will be needed to reveal regional differences. A single number is useful, but a moon is rarely one number all the way around. We can now picture Europa's shell more clearly, even though much remains unseen. The upper layers are cold and brittle, marked by shallow imperfections and immense surface fractures. Farther down, temperature rises. The ice may become stronger in some ways, softer in others, and eventually capable of flowing without melting. Somewhere below the measured conductive region, either directly or beneath an additional convecting layer, the solid roof finally gives way to the dark ocean. That boundary may lie tens of kilometers beneath the plains we crossed earlier. It is distant but not necessarily isolated. Heat can move upward. Stress can move through the shell. Salts and pockets of brine may alter the way the ice deforms. To understand whether anything more than solid ice occupies the space between surface and sea, we must now travel inside the shell itself into a region where frozen material may move almost like a very slow current. The ice beneath Europa's surface may be solid from top to bottom, yet solid does not always mean motionless. Near the surface, where heat escapes easily into space, the ice is extremely cold and behaves like a brittle material. Stress can build until the upper shell fractures, leaving the long lines and paired ridges we've already crossed. Deeper down, however, the temperature gradually rises. The weight of the overlying shell increases the pressure, while heat arriving from the ocean and rocky interior changes how easily the ice can deform. At sufficient warmth, ice can respond to stress without breaking. Its crystals slowly change shape, slide past one another and reorganize. Nothing becomes visibly fluid. There is no rushing current beneath our imagined feet. But over thousands or millions of years, material may travel distances that would seem impossible during a human lifetime. Europa's shell could therefore contain two very different worlds, a cold upper lid that cracks and a warmer interior that bends. Earth's glaciers offer a useful starting image. A glacier feels hard and permanent when touched, yet the entire mass can creep downhill under its own weight. Deep within it, ice flows around obstacles, closes some cavities, and stretches into new forms while remaining frozen. Europa's deeper ice may behave in a related way, although the forces and surroundings are very different. There are no mountain valleys guiding the motion, almost no atmosphere above, and much weaker gravity pulling downward. Instead, Europa's ice is influenced by heat from below, and by tidal stresses that change as the moon circles Jupiter. The rate of deformation also depends strongly on temperature, crystal size impurities, and the amount of stress being applied. A small change in one of these properties can make ice much easier or much harder to move. This is why the shell cannot be described simply as thick or thin. Its behavior matters as much as its depth. If the lower shell becomes warm and mobile enough, it may undergo solid-state convection. Warmer ice near the ocean would be slightly more buoyant and could rise slowly, while cooler, denser ice from above might sink. The process resembles convection in a pot, only in the broadest sense. Europa's ice would not roll visibly, and the circulating material would remain solid rather than bubbling as liquid. A better mental picture is an almost frozen pattern of rising and falling columns, moving so slowly that a mountain could seem hurried beside them. Models show that convection is possible under some combinations of shell thickness, heat flow, grain size, and ice viscosity. Surface pit spots and domes have also been interpreted as possible expressions of warm masses rising within the shell. Yet these features do not prove that convection is currently widespread. Other geological processes could create similar shapes, and the conditions inside the shell are still poorly constrained. The ice is unlikely to be chemically pure. Salts and other materials may enter it when ocean water freezes at the base of the shell, when briny liquid moves through fractures, or when older surface material is carried downward. As water freezes, its crystal structure tends to exclude many dissolved substances. The remaining liquid can therefore become saltier, lowering its freezing temperature and allowing small amounts of brine to survive where pure water would have solidified. On Earth, sea ice can contain narrow channels and pockets of concentrated salty liquid. Europa may also preserve brines, but the resemblance must not be pushed too far. Its shell may be tens of kilometers thick, its temperatures are far lower near the surface, and the chemistry of its ocean is not yet known. Any internal brines could take the form of thin films, scattered inclusions, larger lenses, or temporary reservoirs created by local heating. We do not yet know which of these forms actually exist. A pocket of liquid inside the shell would not necessarily remain in one place. Brine is often denser than relatively pure ice, but its movement would depend on temperature composition surrounding fractures and changes caused by freezing. As part of a reservoir freezes, the remaining liquid can become more concentrated. Pressure may increase. New cracks may form, allowing the brine to migrate sideways downward, or occasionally upward into colder regions where it freezes again. Numerical models suggest that such processes could create moving pockets and perhaps contribute to eruptions at the surface under suitable conditions. But an eruption from a shallow reservoir would not automatically provide a fresh sample of the global ocean. The liquid might have spent a very long time inside the shell, repeatedly freezing, concentrating and reacting with surrounding ice. By the time it reached the surface, it could carry the history of the crust more clearly than the composition of the sea below. The shell may also transport material without preserving it as liquid. Warm ice rising from near the ocean could trap salts or particles and carry them gradually upward. Cooler ice sinking from above might bring radiation-altered compounds into deeper regions. This kind of circulation would matter greatly for habitability, because Europa's surface and seafloor may produce different chemical ingredients. The surface receives energetic particles from Jupiter's magnetic environment, while the rocky interior may provide reduced minerals and other compounds through water-rock reactions. If these materials remain permanently separated, much of their potential chemical energy cannot be used. A convecting shell could help connect them, but the journey might take hundreds of thousands or millions of years, and some compounds would react or transform along the way. Europa may possess pathways through its ice, yet pathways do not have to be open tunnels. They may be slow cycles of freezing, sinking, warming, deforming and rising, so the region between Europa's surface and ocean is probably not empty space concealed beneath a rigid lid. It may be a layered environment with brittle faults above warmer mobile ice below, and chemically unusual pockets scattered between them. Some regions could be quiet for immense periods. Others may be altered by local heat or repeated tidal stress. The shell could preserve ancient ocean material while also creating new chemistry of its own. But each possibility comes with uncertainty. We do not know whether convection occurs everywhere, only in selected regions, or mainly during warmer periods in Europa's past. We do not know how common liquid pockets are or how long they survive. To search for places where this hidden motion may have approached the surface, we must return to Europa's most disordered landscapes. Ahead lies chaos terrain, where familiar ridges break apart and great blocks of ice appear to have lost their original places. Chaos terrain looks as though Europa's surface briefly forgot how to remain a surface. The long ridges and bands that cross much of the Moon give way to irregular regions filled with tilted plates, rough material pits, domes, and fragments of older ground that no longer fit neatly together. In places such as Connemara Chaos, blocks of pre-existing ice appear to have shifted sideways and rotated before becoming surrounded by a younger, more uneven matrix. Some pieces preserve ridges that once continued across neighbouring blocks, allowing their earlier positions to be reconstructed. The result resembles a jigsaw puzzle after several pieces have been turned and pushed apart. But the resemblance explains only the appearance. On Earth, broken sea ice can drift because liquid water lies directly beneath it. On Europa, the global ocean may be separated from the surface by many kilometres of solid ice. The scattered plates therefore do not automatically prove that the shell once opened onto a shallow sea. To form chaos terrain, something must first weaken or disrupt the old surface. One early family of models proposed that heat rising from below could melt through a relatively thin shell, breaking the crust into rafts above exposed or partly exposed water. Liquid or slushy material could then fill the spaces before freezing. This model naturally explains why some blocks look displaced and why the surrounding matrix appears younger. Yet it becomes harder to apply if Europa's shell is thick, particularly if the cold conductive region alone extends through tens of kilometres. Melting all the way from the ocean to the surface would require concentrating and sustaining a considerable amount of heat. It might still occur under unusual conditions, but it may not be the ordinary explanation for every chaos region. The visual simplicity of open water beneath floating blocks is attractive. Europa, unfortunately, is not required to choose the explanation that is easiest to draw. A second possibility begins not with complete melting, but with warm ice rising through colder ice. In this model, a buoyant mass called a diapir moves slowly upward from the warmer lower shell. It remains largely solid, much as deep glacial ice can flow without becoming liquid. As the rising material approaches the brittle upper layers, it pushes them upward, changes the local stress, and carries heat toward the surface. The ground above may arch into a dome fracture around the edges, or become disordered as the underlying ice spreads sideways. Tidal deformation could add further heating inside the rising mass, and make localized melting more likely near its upper boundary. Topographic studies have found that some chaos regions and nearby domes are consistent with this kind of upward movement. But diapirism is not a single finished answer. The size, temperature, buoyancy, and chemical composition of the rising material would determine whether it produces a gentle uplift, a cluster of pits, or a broad region of broken terrain. Another family of models places a body of liquid or partially melted material within the shell, rather than connecting the disturbance directly to the global ocean. Heat arriving from below, concentrated tidal dissipation, or warm rising ice might create a shallow melt lens. Salts would lower the freezing temperature, helping a briny reservoir survive longer than pure water under the same conditions. The roof above the lens could fracture, sag, or collapse as the liquid moved or gradually froze. Older surface blocks might then sink, tilt, or rotate within softened material. This could produce chaos-like topography, without requiring an open passage through the entire shell. Some models of ice collapse over trapped water, reproduce important features of the observed landscape. Yet the depth and size of any such reservoirs remain uncertain. Shallow on Europa might still mean several kilometres below the surface, which is close only by the standards of a moon with a very thick roof. The competing models may not be mutually exclusive. A warm diapir could rise, create partial melting, and feed a brine-rich lens. The lens could spread beneath the brittle lid while tidal stresses fracture the ground above it. Liquid might drain, refreeze, or migrate into new cracks. The surface could collapse after support was lost, leaving blocks embedded in a rougher matrix. Different stages of this sequence might produce different forms of chaos terrain, from regions dominated by recognizable plates to knobbier landscapes where the original surface has been almost completely erased. Studies comparing many chaos regions have found a wide range of shapes and textures rather than one uniform pattern. That variety suggests that the word chaos may describe a family of geological outcomes rather than one repeated event. Europa may have several methods for rearranging its ice, which is impressive for a world that appears so quiet from a distance. Chaos terrain matters because it may bring relatively deep material closer to the surface. Warm ice rising from below could carry salts or other compounds upward. A shallow liquid reservoir might contain material extracted from the shell or less directly from the ocean beneath it. Fractures could expose some of that material before Jupiter's radiation begins altering its chemistry. This makes chaos regions valuable places to examine for evidence of interior surface exchange. But the origin of any compound found there must be treated carefully. Material could come from the global ocean from a temporary reservoir inside the shell, from chemical reactions within the ice, or from particles delivered to the surface from elsewhere. Even when the terrain is young, the exposed substances may have been transformed by radiation. Chaos is therefore a possible message from below, but the message has passed through several hands and arrived without an envelope. For now we can say that Europa's disrupted landscapes record concentrated activity within the frozen shell. They show that the surface has been broken and rearranged, that warmer or mechanically weaker material probably influenced it from beneath, and that shallow liquid may sometimes have played a role. They do not reveal one universal mechanism, and they do not provide an open window into the global ocean. Yet every leading model points downward. Beneath the fractured plates lies warmer ice. Beneath that ice, the evidence leads toward a continuous layer of salty water surrounding the moon. We have followed ridges, tides, magnetic fields, temperature gradients, and broken terrain as far as the shell allows. The next step carries us beyond the solid roof and into Europa's hidden ocean, a sea without sunlight, weather, or any horizon visible from above. At some uncertain depth beneath Europa's fractured plains, the downward journey changes completely. The warmest ice no longer supports its own solid structure, and the frozen roof gives way to liquid water. There may be no sharp visual boundary like the surface of a lake beneath an open sky. The underside of the shell could be irregular, with ridges descending from above pockets, where water freezes onto the ice, and other regions where the shell slowly melts. Beyond that boundary lies a global ocean hidden from sunlight and sealed beneath kilometers of frozen material. Current estimates suggest that this ocean may extend roughly 60 to 150 kilometers deep, though its exact dimensions remain unknown. That would make it far deeper than Earth's average ocean, and give Europa more liquid water than all the seas on our planet combined. The moon is smaller than Earth's moon, yet much of its outer volume may be water. A small world can hide a very large sea. There would be no daylight here, no blue surface overhead, and no waves shaped by wind. Europa has almost no atmosphere, and its ocean never meets an open sky. The only light in our thought experiment comes from an imaginary instrument travelling safely beside us. Without it, the water would remain completely dark. Even the faint sunlight falling on Europa's exterior cannot penetrate more than a tiny fraction of the shell above. This does not make the ocean empty or inactive. Darkness is simply one environmental condition. Water can still move, transport heat, dissolve minerals, and carry chemical compounds without receiving sunlight. Earth's deepest oceans provide a limited comparison, since they also remain dark and experience great pressure. But Earth's ocean communicates with an atmosphere, receives material from continents, and is stirred partly by winds at the surface. Europa's sea is enclosed between ice and rock, Its circulation must be driven by an entirely different arrangement of forces. Pressure increases steadily as we descend. Every layer of water carries the weight of all the water and ice above it. Near the ocean floor, the pressure could be far greater than in Earth's deepest trenches, depending on the ocean's true depth and the thickness of the shell. Yet the situation is moderated somewhat by Europa's weaker gravity. The water column may be much deeper than Earth's, but each layer weighs less than the same layer would on our planet. Under these conditions, liquid water can remain stable across much of the ocean. At still greater pressures, some worlds may form dense varieties of ice at the bottom of their oceans, separating liquid water from the rocky interior. Europa is generally thought to be small enough, and its ocean likely shallow enough in planetary terms for liquid water to contact rock directly. That possible contact is essential. An ocean resting only on high-pressure ice would have fewer opportunities to exchange chemicals with minerals below. The ocean is probably salty, although we do not yet know which salts dominate or how concentrated they are. The induced magnetic field measured by Galileo requires an electrically conductive layer, and dissolved ions in water provide a natural explanation. Compounds containing magnesium, sodium chloride, sulfate carbonate or other ions have all appeared in models of Europa's chemistry, but the available evidence has not selected one simple recipe. The composition may also vary with depth and location. Water freezing onto the base of the shell could leave some dissolved substances behind, making the remaining liquid saltier. Melting ice could dilute nearby water. Reactions with rock might add or remove other compounds over time. Europa's ocean should therefore not be imagined as an enormous container of ordinary seawater copied from Earth. It may have a chemistry with no exact modern equivalent shaped by its rocky interior, its long history and the repeated freezing and melting occurring beneath the shell. Although the ocean is enclosed, it may not be still. Heat rising from below and cooling against the ice above can create differences in water density. Warmer water generally tends to rise while cooler water tends to sink, though salinity can complicate that pattern. Europa's rotation may organize moving water into broad columns or currents that follow the moon's axis. Tidal forces can disturb the ocean, as Jupiter's gravity flexes the surrounding shell and rocky interior. Some models produce vigorous circulation capable of carrying heat from the seafloor toward the ice. Others produce more layered behavior with different regions mixing only slowly. The pattern depends on quantities that remain poorly known, including ocean depth, salt concentration, heating at the seafloor, freezing beneath the shell, and the roughness of both boundaries. We can be confident that a global ocean responds to heat and rotation. We cannot yet draw a reliable map of its currents. The ice ceiling and the water beneath it may continually reshape one another. Where relatively warm ocean water reaches the base of the shell, small amounts of ice may melt. Elsewhere, heat may escape more efficiently, allowing new ice to freeze downward. Freezing rejects many dissolved salts, altering the nearby water and changing its density. Melting introduces fresher water. These local differences could help drive circulation while gradually modifying the shell above. The process resembles the interaction between sea ice and polar oceans on Earth only in outline. Europa has no seasons like ours, no wind, and a shell far thicker than terrestrial sea ice. Its frozen roof may also flex with every orbit, changing stresses at the boundary. Across long periods, the ocean and shell could exchange heat, water, and chemical material in a slow conversation, though we do not yet know how effectively information from the deep ocean reaches the visible surface. For all its scale, the ocean alone does not answer the question that makes Europa so compelling. Liquid water is important because it can dissolve substances, move them between environments, and provide a stable setting for complex chemistry. But water is not a guarantee of habitability, and habitability is not evidence of life. Europa's sea could be too acidic, too alkaline, too chemically uniform, or too limited in usable energy. It could also possess conditions that remained favourable for immense spans of time. To distinguish among those possibilities, we must continue to the deepest part of the journey. Below the black water lies Europa's rocky interior, a boundary where minerals may react with the ocean, and where internal heat may create lasting chemical differences. The ice roof preserves the sea, but the stone beneath it may determine what the sea can become. At the bottom of Europa's hidden ocean, the water is thought to meet a rocky seafloor. This boundary may be one of the most important places on the Moon because liquid water resting against rock can do far more than remain liquid. It can enter fractures, dissolve minerals, carry chemicals away, and return with a composition different from the water that first descended. Europa is thought to contain a metallic core surrounded by a rocky mantle, with the ocean lying above that rock rather than being separated from it by a thick layer of high-pressure ice. We have never observed the seafloor directly, and no measurement has shown us its mountains, valleys, or sediments. Even its roughness is unknown. Yet the likely contact between ocean and stone gives Europa something more scientifically useful than an enormous reservoir of water. It gives the ocean a place where chemistry can be continually altered. The surface ice preserves the sea from space. The seafloor may help keep it chemically alive. Imagine water moving into a crack within the rock. As it travels downward, it may encounter warmer minerals and react with them. Some elements dissolve into the water, while others become locked inside newly formed minerals. The process can change the fluid's acidity, salinity, and chemical balance. On Earth, one important family of reactions occurs when water interacts with certain iron-rich rocks, producing new minerals and sometimes releasing molecular hydrogen. This process is commonly associated with serpentinization. Something broadly similar could occur inside Europa if its rocky mantle contains suitable minerals and if ocean water can circulate through fractured rock. The hydrogen would matter not because it is alive, but because it can store chemical energy. When hydrogen meets a chemically compatible oxidizing substance, the reaction can release energy that living cells might use. Europa's exact mineral composition is uncertain, however, and we do not know whether these reactions occur rapidly, slowly, or hardly at all. The seafloor may be chemically active. It has not yet been chemically sampled. Heat could make this exchange more powerful. Europa's rocky interior contains energy left from its formation, heat produced by the decay of radioactive elements, and possibly additional heat generated by tidal deformation. If parts of the rock remain warm enough, water entering fractures could be heated and become buoyant. It might rise back toward the ocean, carrying dissolved minerals and chemically altered compounds. On Earth, concentrated versions of this circulation form hydrothermal systems, where hot fluids emerge through openings in the sea floor. It is reasonable to investigate whether Europa could host comparable systems, and models suggest that hydrothermal activity, or even localized seafloor volcanism, may be physically possible under some interior conditions. But no vent has been detected there. We should not picture black smokers rising confidently from Europa's seabed as though a camera had already visited them. The most responsible image is quieter water, moving through unseen cracks, exchanging heat and chemistry, with rock perhaps emerging diffusely, perhaps concentrating into vents, and perhaps doing much less than our most active models predict. Earth's hydrothermal environments are useful because they demonstrate that ecosystems do not always depend directly on sunlight. Far below our ocean surface, microorganisms can obtain energy from chemical reactions involving hydrogen-sulfur compounds, methane, iron, and other materials. Larger organisms may then depend on those microbial communities. This discovery changed the older assumption that every ecosystem must ultimately begin with sunlight falling on plants. Yet Earth is not a template that can simply be placed on Europa. Our seafloor is connected to an active planet with plate tectonics, abundant volcanic heat, a complex ocean, and billions of years of biological influence. Europa's rock may be colder, less permeable, or chemically less generous. Its ocean may lack important elements in usable forms. Even when a chemical reaction releases energy, that energy must be available at a useful rate and in the same place as water and nutrients. A planet can possess promising ingredients while storing them on different shelves. The real importance of the seafloor may therefore lie in chemical imbalance. An ocean that reaches complete equilibrium would offer fewer opportunities for energy-releasing reactions. Habitability becomes more plausible when different regions continually produce substances that have not yet reacted with one another. Europa's rocky interior could supply reduced compounds such as hydrogen, while radiation at the surface may create oxidizing compounds within the ice. If some of the surface products eventually travel downward and some seafloor products move upward, they could meet within the ocean and release chemical energy. But the journey between those reservoirs may be difficult. A thick ice shell could slow the delivery of surface oxidants, and a deep ocean could dilute material rising from the bottom. Ocean currents might help transport compounds, but their strength and pattern remain uncertain. The question is not only whether Europa can manufacture useful chemicals, it is whether the moon can bring them together before they are lost, transformed, or spread too thinly. Time adds one final uncertainty. Water rock reactions can gradually alter the seafloor itself, filling fractures with new minerals and reducing the pathways through which water circulates. An initially active system may slow as the most reactive minerals are consumed. New fracturing caused by tides or internal stress could reopen those pathways, exposing fresh rock and allowing chemical exchange to continue. Europa's seafloor might therefore pass through cycles of activity and quiet. It could contain local warm regions separated by immense areas where reactions proceed almost imperceptibly. We do not know whether the ocean is chemically rich throughout, favourable only near the bottom, or limited everywhere by one missing ingredient. What lies where the ocean meets rock is not a confirmed garden of life. It is a boundary where heat, minerals, liquid water, and time may create continuing chemical opportunities. And this brings us to the next question. In a world where sunlight never reaches the sea, how much usable energy could those opportunities actually provide? Europa's ocean exists in permanent darkness, but darkness does not remove the need for energy. It only changes where that energy must come from. On Earth, sunlight supports most familiar ecosystems by allowing plants, algae, and certain microorganisms to store energy in chemical bonds. Beneath Europa's ice, sunlight cannot perform that work. Heat may rise from the rocky interior, and tidal deformation may keep the ocean liquid, but warmth alone is not necessarily useful to living cells. A warm cup of water contains thermal energy, yet that energy is spread through the water and cannot easily be directed into the organized chemical work required for metabolism. Life needs reactions that can proceed from a higher energy arrangement toward a lower energy one. It needs substances that have not already settled into balance. Europa's central question is therefore not simply whether it contains heat. It is whether the moon continually creates chemical differences that something living could exploit. A useful way to picture this is as a natural battery. A battery stores energy by keeping chemically different materials apart until a pathway allows them to react. Europa may possess two broad chemical regions capable of playing similar roles. At the rocky sea floor, water-rock reactions could produce reduced compounds, potentially including molecular hydrogen. At the surface, energetic particles trapped in Jupiter's magnetic environment strike water ice and break molecules apart. The fragments can recombine into oxidizing compounds such as hydrogen peroxide and molecular oxygen. These surface products contain no sign of biology by themselves. They are created through radiation chemistry. Yet if oxidants from above could eventually meet reduced substances from below, their reaction might release energy. The battery comparison has limits, of course. Europa contains no tidy terminals, no wires, and no guarantee that the necessary compounds exist in useful concentrations. The important idea is separation. Chemical energy can remain stored while compatible substances are kept apart. The surface is a surprisingly active chemical factory. Jupiter's magnetic field traps and accelerates charged particles, which continually strike Europa's exposed ice. These particles can split water molecules, eject some material into space, and transform salts or carbon-bearing compounds already present on the surface. Hydrogen atoms are light and may escape more easily, while heavier oxygen-rich products can remain behind. Over long periods, this radiation can create an oxidized upper layer. From the perspective of a surface organism, if such a thing could survive there, the radiation would be intensely damaging. But from the safety of our thought experiment, we can see another possibility. The same environment that makes the exterior hostile may manufacture compounds useful to chemistry in the protected ocean below. Europa's surface could be both a barrier to life and a source of potential energy. The difficulty lies in transporting its products downward through a shell that may be tens of kilometers thick. Fractures, geological recycling, and the slow motion of ice may provide possible routes. Surface material could be buried when bands open and are filled when sections of the shell shift, or when cold ice sinks into warmer regions below. Briny liquid moving through fractures might carry dissolved compounds in either direction. If solid-state convection occurs, it could gradually transport radiation-altered ice downward while bringing warmer interior material upward. None of these processes needs to resemble water flowing through an open pipe. A molecule could spend thousands of years frozen inside one layer, move deeper as the ice deforms, dissolve briefly into a brine pocket, freeze again, and continue its journey much later. By human standards, this is a remarkably inefficient delivery service. Geological time is less concerned about punctuality. What matters is whether enough oxidizing material reaches the ocean before reacting within the shell, being lost to space or becoming trapped in forms that are difficult to use. At the opposite boundary, Europa's rocky seafloor may provide reduced chemicals. Water moving through fresh rock could release hydrogen or other compounds capable of reacting with oxidants. Internal heat might sustain circulation through cracks, exposing new mineral surfaces and preventing the system from reaching complete equilibrium. But this supply is uncertain as well. The rock may not fracture often enough. Reactive minerals may become exhausted or covered by alteration products. Water circulation could be weak, and any useful compounds released at the bottom might be diluted through an ocean perhaps more than 100 kilometers deep. Europa may contain an enormous amount of water, but abundance can sometimes become a disadvantage. A small quantity of chemical fuel dispersed throughout a global sea may be difficult for living systems to collect. Habitability depends not only on whether energy exists, but on whether it is concentrated in accessible places and renewed over meaningful length of time. Ocean circulation could help bring the two chemical reservoirs together. Heat rising from the interior cooling beneath the ice, Europa's rotation and tidal forcing may all drive currents. These currents might carry seafloor products upward and distribute oxidants delivered from the shell. local boundaries could become especially important. Near the seafloor, warm, chemically altered water may mix with colder ocean water. Near the ice ceiling, brines rejected during freezing may sink because of their increased salinity. Each mixing zone could maintain gradients in temperature and composition. On Earth, microorganisms often gather where such gradients are strongest, because that is where useful reactants meet. Yet we cannot assume Europa contains similar communities. We do not know the ocean's acidity nutrient inventory, salt balance, or rates of chemical renewal. Even a promising reaction may release energy too slowly to support much activity. A battery can contain energy and still remain almost impossible to discharge. This leaves Europa in a scientifically fascinating middle ground. It appears to possess liquid water long-term internal heating surface chemistry, driven by radiation, and a rocky boundary where additional reactions may occur. These are important pieces of a potentially habitable system, but the connections among them remain uncertain. A thick, stagnant shell could keep surface oxidants from reaching the ocean. Weak seafloor activity could limit the supply of reduced compounds. Slow circulation might leave the sea chemically uniform, while stronger circulation could create useful meeting places. The question is no longer whether energy exists somewhere on Europa. Energy is present in orbital motion, heat radiation, and chemical bonds. The deeper question is whether that energy becomes organized into lasting chemical opportunities. And before we imagine what might use those opportunities, we must make one distinction very carefully. A world capable of supporting life is not the same as a world where life has begun. Europa may possess water chemistry, internal heat, and a history extending across billions of years. Those qualities make it a compelling place to investigate habitability. But the word habitable is easy to misunderstand. It does not mean that life is present. It does not even mean that life could survive everywhere within the ocean. A habitable environment is simply one in which the physical and chemical conditions might allow some form of life to function, reproduce, and persist. Earth contains many habitable places, yet not every pool, cave, cloud, or patch of soil is occupied in the same way. Some environments contain life only intermittently. Others may contain the necessary ingredients but lack a path by which biology can begin. Europa has not provided an organism a fossil or a confirmed biological signal. What it has provided is a set of conditions worthy of careful examination. The distinction is small in wording and enormous in meaning. Liquid water is the most familiar of those conditions because all known life uses it. Water dissolves many substances, allows molecules to move and interact, helps regulate temperature, and participates directly in biological reactions. Europa appears to have a great deal of it. Yet an ocean can be liquid and still be chemically unfavorable. Its acidity might lie outside the range tolerated by known organisms. Its salts could be present in concentrations that make cellular chemistry difficult. Essential elements might exist but remain locked in minerals or dispersed too thinly to collect. Even the ocean's temperature, though probably suitable for liquid water, may vary between regions and through time. When scientists call Europa an ocean world, they are describing its physical structure. When they call it potentially habitable, they are asking whether the ocean's complete environment could support metabolism. Water opens the question. It does not answer it. Life also requires chemical building materials. On Earth, carbon forms the flexible molecular frameworks used by cells, while hydrogen, oxygen, nitrogen, phosphorus, sulfur, and many other elements perform essential roles. Europa almost certainly contains several of these elements somewhere within its ice ocean or rocky interior. Carbon dioxide has been detected on its surface, particularly in geologically disrupted terrain, and other non-ice materials appear along ridges and bands. But the presence of carbon compounds is not evidence of organisms. Carbon chemistry is common throughout the solar system. Comets, meteorites, planetary atmospheres, and interstellar clouds can all contain organic molecules formed without biology. In science, the word organic usually means carbon-bearing, not living. A moon can possess an impressive collection of ingredients without ever producing a cell. A kitchen containing flour, water, and salt has not necessarily baked anything, and Europa has not left a helpful recipe beside the mixing bowl. Even a favourable mixture of water and elements would still require usable energy. As we have seen, the surface may generate oxidizing compounds, while the seafloor may produce reduced chemicals through water-rock reactions. If those materials meet, they could release energy that hypothetical microorganisms might capture. But the quantity and rate matter. A reaction that releases energy only rarely may support little or no biological activity. Nutrients must also be renewed rather than consumed once and lost. Stable ecosystems generally require cycles that move material through an environment, allowing compounds to be reused or replaced. Europa's tides, ocean circulation, freezing ice, and possible seafloor activity might create such cycles. They might also keep the most useful substances separated by many kilometers. A potentially habitable world is not merely a warehouse of ingredients. It is a working system in which matter and energy must continue to move. Time presents another question. Life on Earth appeared relatively early in our planet's history, but one example cannot reveal how easily life begins elsewhere. The origin of life may occur readily when conditions are suitable, or it may require an exceptionally rare sequence of events. Science does not yet know. Europa's ocean may have persisted for a very long time, providing stability that could allow complex chemistry to develop gradually. On the other hand, its internal conditions may have changed as the moon cooled, its orbit evolved, and its shell thickened or thinned. Periods of stronger tidal heating might have alternated with quieter eras. The ocean could have remained continuously liquid while its chemistry shifted around it. Long duration is useful because it provides opportunity, but time alone does not perform chemistry with a guaranteed result. 1 billion years is generous. It is not a promise. We must also separate prebiotic chemistry from biology. Prebiotic chemistry includes non-living reactions that produce increasingly complex molecules or organized chemical systems. Such processes may be steps toward life, but they are not themselves proof that life has emerged. A biosignature is something that may be produced by organisms and could therefore indicate biology, such as a distinctive molecular pattern, isotopic ratio, or combination of chemicals far from equilibrium. Yet many possible biosignatures can also be created through geological or radiation-driven processes. Confirmation requires ruling out those non-biological explanations. On Europa, that task would be especially difficult because surface radiation modifies compounds after they arrive, while material from the ocean may be mixed with substances formed inside the shell. One unusual molecule would not settle the question. Scientists would need several connected lines of evidence, all pointing toward biology more convincingly than toward chemistry alone. So what might life on Europa look like? The responsible answer is that we do not know whether there is any life to describe. If organisms exist, simple microbial forms are scientifically easier to consider than large animals, because microorganisms can survive with smaller energy supplies and inhabit narrow chemical environments on Earth. But even that comparison can lead imagination too far. Europan biology, if it exists, might use familiar chemistry because the same physical laws apply everywhere, or it might differ in ways we have not anticipated. There is no evidence for forests beneath the ice, luminous creatures in the dark water, or civilizations listening through the shell. Those images belong to fiction, not observation. Europa's genuine mystery is quieter, and in some ways more profound. Somewhere beneath the frozen surface, ordinary matter may have been given water chemistry, energy, and time. Whether those conditions ever crossed the uncertain boundary into life remains completely unknown. To investigate the boundary, scientists must search for material that has escaped from below, carried upward through the ice, or perhaps released into space. The next clues may be waiting in salts, carbon compounds, and the uncertain traces of possible plumes. If material from Europa's ocean ever reaches space, it would offer a remarkable shortcut. Instead of drilling through many kilometers of ice, a spacecraft might pass through vapor or falling particles and examine a sample carried upward naturally. This possibility has made Europa's suspected plumes especially attractive. On Saturn's moon, Enceladus jets of water vapor and ice grains clearly erupt from fractures near the South Pole. Europa has often been pictured as a larger and quieter version of that active world, but the evidence is much less certain. Telescopes and spacecraft have reported several signals that could be explained by temporary releases of water. Other observations, sometimes made with very sensitive instruments, have found nothing. The careful conclusion is not that Europa definitely erupts, nor that it definitely does not. It is that intermittent plumes remain possible, while their existence, frequency, source and strength are still unresolved. One early clue came from ultraviolet observations with the Hubble Space Telescope. Researchers reported emissions near Europa's southern region that were interpreted as the products of water molecules broken apart after being released into space. Later Hubble images taken while Europa passed in front of bright Jupiter showed dark features beyond the moon's edge, as though gas or particles were absorbing some of Jupiter's ultraviolet light. Reanalysis of older Galileo measurements also found magnetic and plasma disturbances that could be consistent with the spacecraft passing through material released near Europa. Ground-based infrared observations later detected water vapor on one occasion, but not during other searches. Each result was intriguing, yet none established a continuously active system like the one at Enceladus. A plume might appear only briefly in a limited region, or under orbital conditions that have not yet been identified. It might also be so faint that even a nearby instrument could miss it. The uncertainty became greater in 2026 when researchers re-examined many years of Hubble ultraviolet data using an improved model of Europa's thin atmosphere and the telescope's observations. They did not recover the localized emission previously interpreted as water vapor activity near the South Pole. The difference arose partly from a revised placement of Europa's disk in the detector images and from accounting more fully for hydrogen already distributed around the Moon. This does not erase every other proposed sign of venting, but it weakens one of the earliest and most influential lines of evidence. Europa may still release water occasionally. It may produce smaller events from shallow reservoirs rather than towering jets connected to the ocean. Or some of the apparent signals may have been created by instrumental effects and Europa's complicated interaction with Jupiter's plasma. Science becomes stronger when old evidence is tested again, even when the new result makes the story less convenient. If plumes exist, their source would matter as much as their presence. Water rising directly from the global ocean could carry information about that ocean's salts, dissolved gases, carbon compounds, and perhaps its water rock chemistry. But a plume could instead begin inside the ice shell. A migrating pocket of brine may freeze around its edges, concentrating salts and increasing pressure until a fracture opens above it. Material could then escape without ever having visited the deep ocean. Such a sample would still be scientifically valuable, It could reveal temperatures, chemical reactions, and liquid reservoirs within the crust. It would not necessarily provide a clean bottle of ocean water. During its passage upward, material might freeze separate into different chemical components, react with the surrounding ice, and lose its most volatile substances. Europa rarely offers a direct message when several layers are available to edit it first. Even without confirmed plumes, the surface itself contains possible messages from below. Spectral observations show that Europa's reddish and yellowish terrains contain materials mixed with water ice. Laboratory experiments suggest that sodium chloride can become yellow or brown after exposure to radiation resembling conditions near Europa, making ordinary salt one possible contributor to the Moon's coloured regions. Other areas may contain hydrated salts, sulfuric acid produced through radiation chemistry, or compounds whose identities remain uncertain. Some substances may have arrived from Jupiter's volcanic moon Io, or formed through interaction with the surrounding plasma. Others may have risen from Europa's own interior. Their location provides an important clue. Materials concentrated along fractures, broad bands, and young chaos terrain are more likely to be related to geological activity than compounds spread evenly across the whole Moon. But even then, the route from ocean to surface may have included several stops within the ice. The James Webb Space Telescope added an especially interesting clue by mapping carbon dioxide on Europa. The carbon dioxide was concentrated in Tara Regio and more weakly in another disrupted region called Powys Regio. Tara Regio is young chaos terrain, where the surface has been broken and rearranged, making it a plausible location for relatively recent exchange with material from inside the Moon. Researchers concluded that the carbon probably had an internal origin, and may ultimately have come from the ocean. Carbon dioxide is not stable for very long on Europa's exposed surface, so its concentration in young terrain suggests geologically recent delivery. Yet this is not a biosignature. Carbon dioxide can be produced through many non-living reactions, and Webb did not detect evidence of a water plume during those observations. The discovery tells us that carbon may travel through Europa's layered system. It does not tell us that biology carried it. Radiation complicates every surface measurement. Energetic particles continually break molecular bonds, create new compounds, darken salts, and remove material into Europa's thin atmosphere. A substance exposed today may no longer resemble the material that first arrived. Scientists must therefore reconstruct the likely starting composition using spectral laboratory experiments, geological context, and models of radiation damage. The most valuable samples may come from young surfaces where interior material has been exposed recently and altered less severely. Europa Clipper will search for those places by combining high-resolution images, compositional maps, thermal observations, radar measurements, magnetic data, and direct measurements of particles and gases around the Moon. It may find active venting, or it may reveal that the best messages remain frozen into the surface. Either result will guide the same larger investigation. To understand Europa, no single clue will be enough. The next step is to see how a spacecraft can assemble many partial views into one picture of the hidden world below. Europa does not offer a convenient inspection hatch. Its ocean is hidden beneath a roof that no existing spacecraft can drill through, and even the shallowest, proposed liquid reservoirs may lie far beyond the reach of an ordinary lander. The next investigation must therefore read the ice from above. NASA's Europa Clipper and the European Space Agency's JUICE spacecraft are already travelling toward the Jupiter system, carrying instruments designed to examine the Moon through light heat. Radio waves, magnetic fields, gravity gas, and dust. Neither mission will descend into the ocean. Neither carries a submarine waiting politely beside the solar panels. Instead, they will search for the physical consequences of what lies below. A buried ocean affects the way Europa flexes. A layered shell changes the path of radar signals. Warm regions alter infrared emission. Salts and carbon-bearing compounds leave spectral patterns in reflected light. The hidden world cannot be photographed directly, but it influences nearly everything around it. Europa Clipper launched in October of 2024 and is following a long path that uses planetary gravity to reshape its journey. After passing Mars in 2025, it is scheduled to return briefly past Earth in December of 2026 before continuing toward Jupiter, where it is expected to arrive in April of 2030. The spacecraft will orbit Jupiter rather than Europa itself. This may sound indirect, but it protects the mission from spending all its time inside the most intense regions of Jupiter's radiation belts. A spacecraft orbiting Europa continuously would receive a damaging radiation dose much more quickly. By following long loops around Jupiter, Clipper can dive close to Europa, gather measurements, and then retreat into a less severe environment to transmit data and prepare for another encounter. Its planned tour includes 49 close flybys, some passing only about 25 kilometers above the surface. Each approach will cross a different region, gradually turning separate narrow observations into a broad investigation of nearly the entire Moon. During those passes, the spacecraft's instruments will work together rather than behave as isolated experiments. Visible light cameras will map ridges, fractures chaos terrain, and impact features at resolutions far better than most earlier images. Stereo views will reveal elevation, allowing scientists to distinguish low plains from raised ridges and collapsed terrain. An infrared mapping spectrometer will identify the distribution of water, ice salts, carbon-bearing compounds, acids, and other surface materials. A thermal imager will search for places that are warmer than their surroundings, perhaps because the ice is unusually thin, recently disturbed, or affected by material rising from below. Ultraviolet observations will examine Europa's thin atmosphere and continue the search for signs of water vapor near the Moon. One instrument can show where a dark band lies. Another can reveal what it contains. A third can ask whether it is warmer than nearby terrain. The method resembles a medical examination that combines several kinds of imaging, though Europa is unlikely to remain still and answer questions about where it hurts. The ice-penetrating radar provides one of the most direct ways to investigate the frozen roof. It will transmit radio waves toward the surface and listen for returning echoes. Some energy will reflect from the top of the ice, while some may travel deeper before encountering fractures, changes in composition, buried layers, brine-rich regions, or perhaps the boundary between solid ice and ocean. By comparing the timing and strength of the echoes, scientists can reconstruct parts of the subsurface structure. Yet radar sounding is not the same as seeing through clear glass. Warm ice salts, surface roughness, and radiation-altered materials can absorb or scatter the signal. In some places, the radar may penetrate deeply. In others, the returning echoes may become difficult to interpret. Even an incomplete view would be valuable. It could reveal whether chaos terrain rests above disturbed ice, whether shallow liquid pockets are plausible, and whether the shell's internal architecture changes from one region to another. Magnetic and gravity measurements will examine the deeper structure on a larger scale. Clipper's magnetometer will measure Europa's induced magnetic response as Jupiter's surrounding field changes. A separate plasma instrument will help distinguish the ocean's signal from distortions caused by charged particles around the Moon. Together, these observations should improve estimates of the ocean's depth and electrical conductivity, which is related to its dissolved salts. The spacecraft's radio link will also serve as a gravity experiment. Tiny changes in Clipper's motion during flybys will reveal variations in Europa's gravitational field, while measurements taken at different points in the Moon's orbit will show how strongly it flexes under Jupiter's tides. A shell floating above liquid water should deform differently from a completely frozen body. None of these techniques will produce one perfect measurement of shell thickness or ocean salinity. Their strength comes from overlap. Radar magnetism, gravity geology, and thermal data can restrict one another's possible explanations. Clipper will also examine material already present in the space around Europa. A mass spectrometer will analyze gases in the Moon's extremely thin atmosphere and any material that might be released by a plume. A dust analyzer will measure tiny solid particles knocked from the surface by micrometeorite impacts, or possibly carried upward by geological activity. These grains may contain salts and other compounds from specific regions, allowing scientists to sample Europa without touching the ground. But even a particle collected during a close flyby will require a careful history. It may have originated at the surface inside the shell, or more remotely from the ocean. Radiation may have changed it before it escaped. Freezing may have separated some ingredients from others. Clipper is not a direct life detection mission, and its instruments are not designed to announce that an organism has been found. Their task is more fundamental to determine whether Europa contains environments where liquid water, useful chemistry, energy, and long-term stability meet. JUICE will add a wider view of the same planetary system. Launched in 2023, it is expected to reach Jupiter in July of 2031, after additional gravity assists including an Earth encounter planned for September of 2026. Its main destination is Ganymede, but its tour also includes 2 close flybys of Europa. During those encounters, JUICE will examine the surface search, the shallow subsurface, with radar measure the plasma and magnetic environment, and look for areas where material may move among the interior surface and space. Clipper will provide repeated Europa-focused passes, while JUICE will compare Europa with Ganymede Callisto and the wider environment shaped by Jupiter. Together the missions will not open the ice. They will do something more patient. They will layer image upon spectrum radar, echo upon magnetic variation, and particle measurement upon gravitational response until Europa's hidden structure becomes harder to conceal. The final part of our journey can then return to the original question and ask what, after all these clues are assembled, is really hiding beneath the frozen surface. So what is really hiding beneath Europa's frozen surface? The clearest answer begins with layers. At the top lies an exposed skin of water ice, intensely cold and continually altered by energetic particles trapped around Jupiter. Across it run reddish fractures, double ridges, broad bands, pits, domes, and regions of chaos terrain, where older ground has been broken and rearranged. Beneath that surface lies a much deeper shell, whose upper portion is cold and brittle, while warmer ice farther down may bend flow and perhaps circulate without fully melting. Salts, fractures, and temporary pockets of brine may be scattered through this shell, although their abundance and arrangement remain uncertain. Then, at some depth, that probably varies from place to place, the solid ice gives way to a global ocean of salty liquid water. Below the ocean lies rock, and perhaps deeper still a metallic centre. Europa is not hiding one simple object. It is hiding an entire planetary system. Some parts of that system are supported by strong evidence. We know that Europa's surface is dominated by water ice, and that it has been geologically renewed. We know that Jupiter's gravity repeatedly deforms the Moon and supplies internal heat through tidal processes. We know that Galileo measured an induced magnetic response best explained by a global electrically conductive layer, with salty water providing the leading interpretation, We know that the surface contains carbon dioxide and other non-ice materials, some concentrated in young disrupted terrain. These observations do not reveal the ocean directly, but they agree with one another. The geology suggests movement above a mechanically separate layer. The magnetic field suggests a global conductor. The tides provide a source of heat. Europa's hidden ocean is therefore not an imaginative addition to an otherwise empty moon. It is the explanation that allows several independent clues to fit together. Other details remain supported possibilities rather than established facts. The lower ice may convect, slowly carrying warmer material upward and colder material downward. Briny reservoirs may form inside the shell, migrate through fractures, freeze and reform. Chaos terrain may develop when warm ice rises, when shallow melt weakens the surface, or when several processes operate together. Surface oxidants created by radiation may sometimes move downward, while reduced compounds produced by water-rock reactions may move upward from the seafloor. If these substances meet, they could provide chemical energy. Hydrothermal circulation may occur within fractures in the rocky interior. None of these possibilities requires biology, and none has yet been observed directly. They are models built from known physics laboratory experiments, comparisons with Earth, and the limited measurements available from spacecraft and telescopes. Europa may use some of these processes, all of them, or combinations we've not yet understood. And then we reach what remains unknown. We do not know the ocean's exact depth, salinity, acidity, circulation, or nutrient content. We do not know whether the ice shell has one dominant thickness or changes greatly across the moon. We do not know how often material travels between the surface and the ocean, or whether most compounds become trapped and transformed within the shell. We do not know whether active hydrothermal systems exist on the seafloor. We do not know whether Europa produces water vapor plumes, how often they might appear, or whether they begin in the global ocean or in shallower reservoirs. Most importantly, we have no evidence that life exists there. Europa may be habitable in some regions and sterile everywhere. It may contain prebiotic chemistry that never crossed into biology, or it may contain environments that have remained chemically active for billions of years without leaving a signal we can recognize from above. This uncertainty does not make Europa less interesting. It makes the moon scientifically honest. The surface gives us enough information to ask precise questions, but not enough to pretend that the answers have already arrived. Europa Clipper and JUICE will improve the picture by studying the shell composition, magnetic environment, gravity, temperature, particles, and possible gases around the moon. They may discover shallow structures inside the ice. They may identify young deposits carrying material from below. They may measure the ocean's properties more accurately or find evidence that the shell is more varied than current models suggest. They may detect active venting, or they may show that Europa is quieter than expected. No single observation is likely to reveal everything. The hidden world will emerge gradually through several imperfect measurements that become more powerful when they agree. Return now to the image with which we began, a pale moon moving beside the enormous face of Jupiter, crossed by a single dark fracture. At first, that line seemed like a mark on an otherwise sealed surface. We can now see it differently. It belongs to a shell, bent by gravity, warmed from below and altered through time. It may contain salts, or material transported from deeper regions, though it may not reach the global ocean directly. Beneath it, the ice changes from brittle to mobile. Beneath that, liquid water surrounds the rocky interior, and at the deepest boundary, the ocean may exchange heat and chemistry with stone. The fracture is not proof of life, and not necessarily an open door. It is simply one visible expression of a moon whose interior has never become entirely still. What Europa hides then is more than an ocean. It hides connections. Connections between Jupiter's gravity and heat inside the Moon, between radiation at the surface and chemistry within the ice, between liquid water and minerals at the seafloor, between ancient orbital motion and landscapes that may have changed comparatively recently. Whether those connections are strong enough to create a habitable environment remains one of the most important unanswered questions in planetary science. Whether life has ever used them is a question still farther away. For now, Europa keeps its ocean beneath the ice revealing itself only through faint magnetic responses, fractured planes, unusual compounds, and the slow bending of a frozen world. And here at the edge of what can currently be known, we can let the journey become quiet again. Jupiter and Europa continue moving whether we watch them or not. The tides continue their patient work. Heat rises slowly. Ice shifts by distances too small to notice in a night. Somewhere beneath the pale surface, a global sea remains untouched by sunlight, perhaps circulating above rock, perhaps carrying chemistry from one hidden boundary to another. Outside your own window, Jupiter may be only a point of light, and Europa far too small to see. Yet the ocean is there in the evidence waiting beneath a moon that once appeared sealed shut. Nothing more needs to be solved tonight. The question can remain beneath the ice, and you can rest above it.